It is threaded on one end for a propeller hub nut. The thrust bearing, which absorbs propeller thrust, is located around the shaft and transmits the thrust to the nose section housing. The shaft is threaded for attaching the thrust bearing retaining nut. On the portion protruding from the housing, between the two sets of threads, splines are located to receive the splined propeller hub. The shaft is generally machined from a steel alloy forging throughout its length. The propeller shaft may be connected by reduction gearing to the engine crankshaft, but in smaller engines the propeller shaft is simply an extension of the engine crankshaft. End of page 1 to 24. To turn the propeller shaft, the engine crankshaft must revolve. Flanged propeller shafts are used on most modern reciprocating and turboprop engines. One end of the shaft is flanged with drilled holes to accept the propeller mounting bolts. The installation may be a short shaft with internal threading to accept the distributor valve to be used with a controllable propeller. The flanged propeller shaft is a very common installation on most propeller-driven aircraft. Reciprocating engine operating principles. The relationships between pressure, volume, and temperature of gases are the basic principles of engine operation. An internal combustion engine is a device for converting heat energy into mechanical energy. Gasoline is vaporized and mixed with air, forced or drawn into a cylinder, compressed by a piston, and then ignited by an electric spark. The conversion of the resultant heat energy into mechanical energy and then into work is accomplished in the cylinder. Figure 1.35 illustrates the various engine components necessary to accomplish this conversion and also presents the principal terms used to indicate engine operation. The operating cycle of an internal combustion reciprocating engine includes the series of events required to induct, compress, ignite, and burn, causing expansion of the air-fuel charge in the cylinder and to scavenge or exhaust the byproducts of the combustion process. When the compressed mixture is ignited, the resultant gases of combustion expand very rapidly and force the piston to move away from the cylinder head. This downward motion of the piston, acting on the crankshaft through the connecting rod, is converted to a circular or rotary motion by the crankshaft. A valve in the top or head of the cylinder opens to allow the burned gases to escape, and the momentum of the crankshaft and the propeller forces the piston back up in the cylinder where it is ready for the next event in the cycle. Another valve in the cylinder head then opens to let in a fresh charge of the air-fuel mixture. The valve allowing for the escape of the burning exhaust gases is called the exhaust valve, and the valve which lets in the fresh charge of the air-fuel mixture is called the intake valve. These valves are opened and closed mechanically at the proper times by the valve operating mechanism. Therefore, the order of the 5 events of a 4-stroke cycle engine are intake, compression, ignition, power, and exhaust. The bore of a cylinder is its inside diameter. The stroke is the distance the piston moves from one end of the cylinder to the other, specifically from top dead center, TDC, to bottom dead center, BDC, or vice versa. Figure 1.35 Operating cycles. There are several operating cycles in use. 1. 4-stroke. 2. 2-stroke. 3. Rotary. 4. Diesel. 4-stroke cycle. The vast majority of certified aircraft reciprocating engines operate on the 4-stroke cycle, sometimes called the Otto cycle after its originator, a German physicist. The 4-stroke cycle engine has many advantages for use in aircraft. One advantage is that it lends itself readily to high performance through supercharging. In this type of engine, 4 strokes are required to complete the required series of events or operating cycle of each cylinder. Figure 1.36 2 complete revolutions of the crankshaft, 720 degrees, are required for the 4 strokes, thus, each cylinder in an engine of this type fires once in every 2 revolutions of the crankshaft. In the following discussion of the 4-stroke cycle engine operation, note that the timing of the ignition and the valve events vary considerably in different engines. End of page 1 to 25. Many factors influence the timing of a specific engine, and it is most important that the engine manufacturer's recommendations in this respect be followed in maintenance and overhaul. The timing of the valve and ignition events is always specified in degrees of crankshaft travel. It should be remembered that a certain amount of crankshaft travel is required to open a valve fully, therefore, the specified timing represents the start of opening rather than the full open position of the valve. An example valve timing chart can be seen in Figure 1.37. Intake stroke. During the intake stroke, the piston is pulled downward in the cylinder by the rotation of the crankshaft. This reduces the pressure in the cylinder and causes air under atmospheric pressure to flow through the carburetor, which meters the correct amount of fuel. The air-fuel mixture passes through the intake pipes and intake valves into the cylinders. The quantity or weight of the air-fuel charge depends upon the degree of throttle opening. The intake valve is open considerably before the piston reaches TDC on the exhaust stroke, in order to induce a greater quantity of the air-fuel charge into the cylinder and thus increase the horsepower. The distance the valve may be opened before TDC, however, is limited by several factors, such as the possibility that hot gases remaining in the cylinder from the previous cycle may flash back into the intake pipe and the induction system. In all high-power aircraft engines, both the intake and the exhaust valves are off the valve seats at TDC at the start of the intake stroke. As mentioned above, the intake valve opens before TDC on the exhaust stroke, valve lead, and the closing of the exhaust valve is delayed considerably after the piston has passed TDC and has started the intake stroke, valve lag. This timing is called valve overlap and is designed to aid in cooling the cylinder internally by circulating the cool incoming air-fuel mixture, to increase the amount of the air-fuel mixture induced into the cylinder, and to aid in scavenging the byproducts of combustion from the cylinder. The intake valve is timed to close about 50 degrees to 75 degrees past BDC on the compression stroke, depending upon the specific engine, to allow the momentum of the incoming gases to charge the cylinder more completely. Because of the comparatively large volume of the cylinder above the piston when the piston is near BDC, the slight upward travel of the piston during this time does not have a great effect on the incoming flow of gases. This late timing can be carried too far because the gases may be forced back through the intake valve and defeat the purpose of the late closing. End of page 1-26. Compression stroke. After the intake valve is closed, the continued upward travel of the piston compresses the air-fuel mixture to obtain the desired burning and expansion characteristics. The charge is fired by means of an electric spark as the piston approaches TDC. The time of ignition varies from 20 degrees to 35 degrees before TDC, depending upon the requirements of the specific engine to ensure complete combustion of the charge by the time the piston is slightly past the TDC position. Many factors affect ignition timing, and the engine manufacturer has expended considerable time and research and testing to determine the best setting. All engines incorporate devices for adjusting the ignition timing, and it is most important that the ignition system be timed according to the engine manufacturer's recommendations. Power stroke. As the piston moves through the TDC position at the end of the compression stroke and starts down on the power stroke, it is pushed downward by the rapid expansion of the burning gases within the cylinder head with a force that can be greater than 15 tons, 30,000 psi, at maximum power output of the engine. The temperature of these burning gases may be between 3,000 degrees Fahrenheit and 4,000 degrees Fahrenheit. As the piston is forced downward during the power stroke by the pressure of the burning gases exerted upon it, the downward movement of the connecting rod is changed to rotary movement by the crankshaft. Then, the rotary movement is transmitted to the propeller shaft to drive the propeller. As the burning gases are expanded, the temperature drops to within safe limits before the exhaust gases flow out through the exhaust port. The timing of the exhaust valve opening is determined by, among other considerations, the desirability of using as much of the expansive force as possible and of scavenging the cylinder as completely and rapidly as possible. The valve is open considerably before BDC on the power stroke, on some engines at 50 degrees and 75 degrees before BDC, while there is still some pressure in the cylinder. This timing is used so that the pressure can force the gases out of the exhaust port as soon as possible. This process frees the cylinder of waste heat after the desired expansion has been obtained and avoids overheating the cylinder and the piston. Thorough scavenging is very important, because any exhaust products remaining in the cylinder dilute the incoming air-fuel charge at the start of the next cycle. Exhaust stroke. As the piston travels through BDC at the completion of the power stroke and starts upward on the exhaust stroke, it begins to push the burned exhaust gases out the exhaust port. The speed of the exhaust gases leaving the cylinder creates a low pressure in the cylinder. This low or reduced pressure speeds the flow of the fresh air fuel charge into the cylinder as the intake valve is beginning to open. The intake valve opening is timed to occur at 8 degrees to 55 degrees before TDC on the exhaust stroke on various engines. Two-stroke cycle. The two-stroke cycle engine has re-emerged and is being used in ultralight, light sport, and many experimental aircraft. As the name implies, two-stroke cycle engines require only one upstroke and one downstroke of the piston to complete the required series of events in the cylinder. Thus, the engine completes the operating cycle in one revolution of the crankshaft. The intake and exhaust functions are accomplished during the same stroke. These engines can be either air or water-cooled and generally require a gear reduction housing between the engine and propeller. Rotary cycle. The rotary cycle has a three-sided rotor that turns inside an elliptical housing, completing 3 of the 4 cycles for each revolution. These engines can be single-rotor or multi-rotor and can be air or water-cooled. They are used mostly with experimental and light aircraft. Vibration characteristics are also very low for this type of engine. Diesel cycle. The diesel cycle depends on high compression pressures to provide for the ignition of the air-fuel charge in the cylinder. As air is drawn in the cylinder, it is compressed by a piston and, at maximum pressure, fuel is sprayed in the cylinder. At this point, the high pressure and temperature in the cylinder causes the fuel to burn, increasing the internal pressure of the cylinder. This drives the piston down, turning or driving the crankshaft. Water and air-cooled engines that can operate on jet A fuel, kerosene, use a version of the diesel cycle. There are many types of diesel cycles in use, including 2-stroke and 4-stroke diesels. Reciprocating engine power and efficiencies. All aircraft engines are rated according to their ability to do work and produce power. This section presents an explanation of work and power and how they are calculated. Also discussed are the various efficiencies that govern the power output of a reciprocating engine. Work. A physicist defines work as force times distance. Work done by a force acting on a body is equal to the magnitude of the force multiplied by the distance through which the force acts. Work, W, equals force, F, x distance, D. End of page 1 to 27. Work is measured by several standards. The most common unit is called foot-pound, FTLB. If a 1-pound mass is raised 1 foot, 1 FTLB of work has been performed. The greater the mass is and or the greater the distance is, the greater the work performed. Horsepower. The common unit of mechanical power is the horsepower, HP. Late in the 18th century, James Watt, the inventor of the steam engine, found that an English workhorse could work at the rate of 550 FTLB per second, or 33,000 FTLB per minute, for a reasonable length of time. From his observations came the unit of horsepower, which is the standard unit of mechanical power in the English system of measurement. To calculate the HP rating of an engine, divide the power developed in FTLB per minute by 33,000, or the power in FTLB per second by 550. 1 HP equals FTLB PR minute divided by 33,000 or FTLB PR second divided by 550. As stated above, work is the product of force and distance, and power is work per unit of time. Consequently, if a 33,000 pounds weight is lifted through a vertical distance of 1 foot in 1 minute, the power expended is 33,000 FTLB per minute, or exactly 1 horsepower. Work is performed not only when a force is applied for lifting, force may be applied in any direction. If a 100 pounds weight is dragged along the ground, a force is still being applied to perform work, although the direction of the resulting motion is approximately horizontal. The amount of this force would depend upon the roughness of the ground. If the weight were attached to a spring scale graduated in pounds, then dragged by pulling on the scale handle, the amount of force required could be measured. Assume that the force required is 90 pounds, and the 100 pounds weight is dragged 660 feet in 2 minutes. The amount of work performed in the 2 minutes is 59,400 FTLB or 29,700 FTLB per minute. Since 1 horsepower is 33,000 FTLB per minute, the HP expended in this case is 29,700 divided by 33,000, or 0.9 horsepower. Piston displacement. When other factors remain equal, the greater the piston displacement, the greater the maximum horsepower an engine is capable of developing. When a piston moves from BDC to TDC, it displaces a specific volume. The volume displaced by the piston is known as piston displacement and is expressed in cubic inches for most American-made engines and cubic centimeters for others. The piston displacement of one cylinder may be obtained by multiplying the area of the cross-section of the cylinder by the total distance the piston moves in the cylinder in one stroke. For multi-cylinder engines, this product is multiplied by the number of cylinders to get the total piston displacement of the engine. Since the volume, V, of a geometric cylinder equals the area, A, of the base multiplied by the height, H, it is expressed mathematically as follows. V equals A times H. The area of the base is the area of the cross-section of the cylinder. Area of a circle. To find the area of a circle, it is necessary to use a number called pi symbol. This number represents the ratio of the circumference to the diameter of any circle. Pi cannot be stated exactly because it is a never-ending decimal. It is 3.1416 expressed to 4 decimal places, which is accurate enough for most computations. The area of a circle, as in a rectangle or triangle, must be expressed in square units. The distance that is 1/2 the diameter of a circle is known as the radius. The area of any circle is found by squaring the radius, r, and multiplying by pi. The formula is as follows. A equals pi times r2. The radius of a circle is equal to 1/2 the diameter. Example. R equals d divided by 2. Compute the piston displacement of the PWA 14-cylinder engine having a cylinder with a 5.5-inch diameter and a 5.5-inch stroke. Formulas required are: R equals d divided by 2. A equals pi times r2. V equals A times h. Total V equals Vxn, number of cylinders. Substitute values into these formulas and complete the calculation. End of page 1 to 28. R equals d divided by 2 is equal to 5.5 inches divided by 2 is equal to 2.75 inchs. A equals pi times r2 equals 3.1416 times 2.75 and times 2.75 and A equals 3.1416 times 7.5625 square inches in 2 equals 23.7584 in 2. V equals A times H equals 23.7584 in 2 times 5.5 and equals 130.6712 cubic inches in 3. Total V equals V times N equals 130.6712 in 3 times 14. Total V equals 1829.3968 in 3. Rounded off to the next whole number, total piston displacement equals 1,829 cubic inches. Another method of calculating the piston displacement uses the diameter of the piston instead of the radius in the formula for the area of the base. A equals 1/4 times pi times d2. Substituting A is equal to 1/4 times 3.1416 times 5.5 and times 5.5 in. A equals 0.7854 times 30.25 in 2. A equals 23.758 in 2. From this point on, the calculations are identical to the preceding example. Compression ratio. All internal combustion engines must compress the air-fuel mixture to receive a reasonable amount of work from each power stroke. The air-fuel charge in the cylinder can be compared to a coil spring in that the more it is compressed, the more work it is potentially capable of doing. The compression ratio of an engine is a comparison of the volume of space in a cylinder when the piston is at the bottom of the stroke to the volume of space when the piston is at the top of the stroke. Figure 1.38. This comparison is expressed as a ratio, hence the term compression ratio. Compression ratio is a controlling factor in the maximum horsepower developed by an engine, but it is limited by present-day fuel grades and the high engine speeds and manifold pressures required for takeoff. For example, if there are 140 cubic inches of space in the cylinder when the piston is at the bottom and there are 20 cubic inches of space when the piston is at the top of the stroke, the compression ratio would be 140 to 20. If this ratio is expressed in fraction form, it would be 140/20 or 7 to 1, usually represented as 7 to 1. The limitations placed on compression ratios, manifold pressure, and the manifold pressure's effect on compression pressures has a major effect on engine operation. Manifold pressure is the average absolute pressure of the air or air-fuel charge in the intake manifold and is measured in units of inches of mercury, Hg. Manifold pressure is dependent on engine speed, throttle setting, and the degree supercharging. The operation of the supercharger increases the weight of the charge entering the cylinder. When a true supercharger is used with the aircraft engine, the manifold pressure may be considerably higher than the pressure of the outside atmosphere. The advantage of this condition is that a greater amount of charge is forced into a given cylinder volume, and a greater output of horsepower results. Compression ratio and manifold pressure determine the pressure in the cylinder in that portion of the operating cycle when both valves are closed. The pressure of the charge before compression is determined by manifold pressure, while the pressure at the height of compression, just prior to ignition, is determined by manifold pressure times the compression ratio. For example, if an engine were operating at a manifold pressure of 30 Hg with a compression ratio of 7 to 1, the pressure at the instant before ignition would be approximately 210 Hg. However, at a manifold pressure of 60 Hg, the pressure would be 420 Hg. Without going into great detail, it has been shown that the compression event magnifies the effect of varying the manifold pressure, and the magnitude of both affects the pressure of the fuel charge just before the instant of ignition. If the pressure at this time becomes too high, pre-ignition or detonation occur and produce overheating. Pre-ignition is when the fuel air charge starts to burn before the spark plug fires. Detonation occurs when the fuel air charge is ignited by the spark plug, but instead of burning at a controlled rate, it explodes, causing cylinder temperatures and pressures to spike very quickly. If this condition exists for very long, the engine can be damaged or destroyed. One of the reasons for using engines with high compression ratios is to obtain long-range fuel economy, to convert more heat energy into useful work than is done in engines of low compression ratio. Since more heat of the charge is converted into useful work, less heat is absorbed by the cylinder walls. This factor promotes cooler engine operation, which in turn increases the thermal efficiency. Here again, a compromise is needed between the demand for fuel economy and the demand for maximum horsepower without detonation. Some manufacturers of high compression engines suppress detonation at high manifold pressures by using high octane fuel and limiting maximum manifold pressure. End of page 1 to 29. Indicated horsepower. The indicated horsepower produced by an engine is the horsepower calculated from the indicated mean effective pressure and the other factors which affect the power output of an engine. Indicated horsepower is the power developed in the combustion chambers without reference to friction losses within the engine. This horsepower is calculated as a function of the actual cylinder pressure recorded during engine operation. To facilitate the indicated horsepower calculations, a mechanical indicating device, such as is attached to the engine cylinder, captures the actual pressure existing in the cylinder during the complete operating cycle. This pressure variation can be represented by the kind of graph shown in Figure 1.39. Notice that the cylinder pressure rises on the compression stroke, reaches a peak after top center, and decreases as the piston moves down on the power stroke. Since the cylinder pressure varies during the operating cycle, an average pressure, line AB, is computed. This average pressure, if applied steadily during the time of the power stroke, would do the same amount of work as the varying pressure during the same period. This average pressure is known as indicated mean effective pressure and is included in the indicated horsepower calculation with other engine specifications. If the characteristics and the indicated mean effective pressure of an engine are known, it is possible to calculate the indicated horsepower rating. The indicated horsepower for a 4-stroke cycle engine can be calculated from the following formula, in which the letter symbols in the numerator are arranged to spell the word plank to assist in memorizing the formula. Indicated horsepower equals plank divided by 3300, where P equals indicated mean effective pressure, in psi. L equals length of the stroke, in feet or in fractions of a foot. A equals area of the piston head or cross-sectional area of the cylinder in square inches. N equals number of power strokes per minute, RPM divided by 2. K equals number of cylinders. In the formula above, the area of the piston multiplied by the indicated mean effective pressure gives the force acting on the piston in pounds. This force multiplied by the length of the stroke in feet gives the work performed in 1 power stroke, which, multiplied by the number of power strokes per minute, gives the number of FTLB per minute of work produced by one cylinder. Multiplying this result by the number of cylinders in the engine gives the amount of work performed, in FTLB, by the engine. Since HP is defined as work done at the rate of 33,000 FTLB per minute, the total number of FTLB of work performed by the engine is divided by 33,000 to find the indicated horsepower. End of page 1 to 30. Example. Given P equals 1.65 lb/2. L equals 0.5 feet. A equals 5.5 inches. N equals 1,500. K equals 12. Indicated HP equals plank divided by 33,000 foot-pound per minute. Find indicated HP. A is found by using the equation A equals 1/4 TMES pi times D2. A is equal to 1/4 times 3.1416 times 5.5 in times 5.5 in equals 23.76 in 2. N is found by multiplying the RPM by 1/2. N equals 1/2 times 3,000 is equal to 1,500 RPM. Now, substituting in the formula. Indicated HP equals 1.65 lb/2 times 0.5 in times 23.76 in 2 times 1,500 revolutions per minute times 12. Divided by 33,000 foot-pounds per minute. Indicated HP equals 1,069.123. Brake horsepower. The indicated horsepower calculation discussed in the preceding paragraph is the theoretical power of a frictionless engine. The total horsepower lost in overcoming friction must be subtracted from the indicated horsepower to arrive at the actual horsepower delivered to the propeller. The power delivered to the propeller for useful work is known as brake horsepower, BHP. The difference between indicated and brake horsepower is known as friction horsepower, which is the horsepower required to overcome mechanical losses, such as the pumping action of the pistons, the friction of the pistons, and the friction of all other moving parts. The measurement of an engine's BHP involves the measurement of a quantity known as torque or twisting moment. Torque is the product of a force and the distance of the force from the axis about which it acts, or torque equals force times distance. Torque is a measure of load and is properly expressed in pound-inches, lb/in, or pound-feet, lb/ft. Torque should not be confused with work, which is expressed in inch-pounds, in lb, or foot-pounds, ft/lb. There are numerous devices for measuring torque, such as a dynamometer or a torque meter. One very simple type of device that can be used to demonstrate torque calculations is the Prony brake. Figure 1:40. All of these torque measuring devices are usable to calculate power output of an engine on a test stand. It consists essentially of a hinged collar, or brake, which can be clamped to a drum spline to the propeller shaft. The collar and drum form a friction brake, which can be adjusted by a wheel. An arm of a known length is rigidly attached to or is a part of the hinged collar and terminates at a point that rests on a set of scales. As the propeller shaft rotates, it tends to carry the hinged collar of the brake with it and is prevented from doing so only by the arm that rests on the scale. The scale indicates the force necessary to arrest the motion of the arm. If the resulting force registered on the scale is multiplied by the length of the arm, the resulting product is the torque exerted by the rotating shaft. For example, if the scale registers 200 pounds and the length of the arm is 3.18 feet, the torque exerted by the shaft is 200 pounds times 3.18 feet equals 636 lb/ft. Once the torque is known, the work done per revolution of the propeller shaft can be computed without difficulty by the equation. Work per revolution equals 2 times pi times torque. End of page 1 to 31. If work per revolution is multiplied by the RPM, the result is work per minute, or power. If the work is expressed in FTLB per minute, this quantity is divided by 33,000. The result is the brake horsepower of the shaft. Power equals work per revolution times RPM. BHP equals work per revolution times RPM divided by 33,000. 2 times pi times or times force on scales, lb, times length of arm, feet, times RPM. Divided by 33,000. Example. Given. Force on scales equals 200 pounds. Length of arm equals 3.18 feet. RPM equals 3000. PYE equals 3.1416. Find BHP substituting in equation. BHP equals 6.2832 times 200 times 3.18 times 3000 divided by 33,000. Equals 362.2. Equals 363. As long as the friction between the brake collar and propeller shaft drum is great enough to impose an appreciable load on the engine, but is not great enough to stop the engine, it is not necessary to know the amount of friction between the collar and drum to compute the BHP. If there were no load imposed, there would be no torque to measure, and the engine would run away. If the imposed load is so great that the engine stalls, there may be considerable torque to measure, but there is no RPM. In either case, it is impossible to measure the BHP of the engine. However, if a reasonable amount of friction exists between the brake drum and the collar and the load is then increased, the tendency of the propeller shaft to carry the collar and arm about with it becomes greater, thus imposing a greater force upon the scales. As long as the torque increase is proportional to the RPM decrease, the horsepower delivered at the shaft remains unchanged. This can be seen from the equation in which 2 pi r and 33,000 are constants and torque and RPM are variables. If the change in RPM is inversely proportional to the change in torque, their product remains unchanged, and BHP remains unchanged. This is important. It shows that horsepower is the function of both torque and RPM, and can be changed by changing either torque, RPM, or both. Friction horsepower. Friction horsepower is the indicated horsepower minus brake horsepower. It is the horsepower used by an engine in overcoming the friction of moving parts, drawing in fuel, expelling exhaust, driving oil and fuel pumps, and other engine accessories. On modern aircraft engines, this power loss through friction may be as high as 10 to 15% of the indicated horsepower. End of page 1 to 32. Friction and brake mean effective pressures. The indicated mean effective pressure, IMEP, discussed previously, is the average pressure produced in the combustion chamber during the operating cycle and is an expression of the theoretical, frictionless power known as indicated horsepower. In addition to completely disregarding power loss to friction, indicated horsepower gives no indication of how much actual power is delivered to the propeller shaft for doing useful work. However, it is related to actual pressures that occur in the cylinder and can be used as a measure of these pressures. To compute the friction loss and net power output, the indicated horsepower of a cylinder may be thought of as two separate powers, each producing a different effect. The first power overcomes internal friction, and the horsepower thus consumed is known as friction horsepower. The second power, known as brake horsepower, produces useful work at the propeller. That portion of IMEP that produces brake horsepower is called brake mean effective pressure, BMEP. The remaining pressure used to overcome internal friction is called friction mean effective pressure, FMEP. Figure 1.41. IMEP is a useful expression of total cylinder power output, but is not a real physical quantity. Likewise, FMEP and BMEP are theoretical but useful expressions of friction losses and net power output. Although BMEP and FMEP have no real existence in the cylinder, they provide a convenient means of representing pressure limits or rating engine performance throughout its entire operating range. There is an operating relationship between IMEP, BMEP, and FMEP. One of the basic limitations placed on engine operation is the pressure developed in the cylinder during combustion. In the discussion of compression ratios and indicated mean effective pressure, it was found that, within limits, increased pressure resulted in increased power. It was also noted that if the cylinder pressure were not controlled within close limits, it would impose dangerous internal loads that might result in engine failure. Therefore, it is important to have a means of determining these cylinder pressures as a protective measure and for efficient application of power. If the BHP is known, the BMEP can be computed by means of the following equation. BMEP equals BHP times 33,000 divided by length. Given BHP equals 1,000. Stroke equals 6 inches. Bore equals 5.5 inches. RPM equals 3,000. Number of cycles equals 12. Find BMEP. Find length of stroke, inches and feet. L equals 6 inches equals 0.5 feet. Find area of cylinder bore. A equals 1/4 times pi times or times D2. A equals 1/4 times 3.1416 times 5.5 and times 5.5 in. A equals 23.76 in 2. Find number of power strokes per min. N equals 1/2 times RPM. N equals 1/2 times 3,000. N equals 1,500. Then, substituting in the equation. BMEP equals 1,000 brake horsepower times 33,000 FTLB/min divided by 0.5 foot times 23.76 in 2 times. 1,500 strokes/min times 12. Equals 154.32 lb/in2. Thrust horsepower. Thrust horsepower can be considered the result of the engine and the propeller working together. If a propeller could be designed to be 100% efficient, the thrust and the BPH would be the same. However, the efficiency of the propeller varies with the engine speed, attitude, altitude, temperature, and airspeed. Thus, the ratio of the thrust horsepower in the BHP delivered to the propeller shaft will never be equal. For example, if an engine develops 1,000 brake horsepower, and it is used with a propeller having 85% efficiency, the thrust horsepower of that engine-propeller combination is 85% of 1,000 or 850 thrust HP. Of the 4 types of horsepower discussed, it is the thrust horsepower that determines the performance of the engine-propeller combination. Efficiencies. Thermal efficiency. Any study of engines and power involves consideration of heat as the source of power. The heat produced by the burning of gasoline in the cylinders causes a rapid expansion of the gases in the cylinder, and this, in turn, moves the pistons and creates mechanical energy. End of page 1 to 33.